In this video, we're going to go over confidence intervals and just give a little bit more of a visual on the process of estimating a confidence interval. So I'm going to go ahead and share my screen with you. Let's see here. And so on this screen right here, we've got this worksheet that we're going to go through really quick. First of all, confidence intervals. We will you are estimating a population parameter such as a population mean by using a statistic. So technically you can estimate any population parameter, but in this course, really all that we're doing is estimating a population mean or a population proportion. You could also technically estimate a population standard deviation if you take a whole bunch of standard deviations, or really any population parameter at all. But right now we're going to do population means and population proportions. So for population mean and what we're doing here is accuracy of that estimation depends on three things: sample size, desired level of confidence, and the population or sample standard deviation of the estimated value. And then if you guys want to also pull up another resource that you have, I gave you guys this super cool decision tree, and this decision tree helps you to determine, hey, what is it that I want to do? Do I want to calculate a confidence interval around a mean or around a proportion? And then if I want to calculate it around a mean, do I need to calculate the sample size, which we'll get to in just a minute, or the margin of error? So once you determine, hey, I want to calculate the margin of error, then you come over here and you say, okay, do I know the population standard deviation or do I not know the population standard deviation? And based on what you know, if you know the population standard deviation, you can follow this. If you do not know the population standard deviation, you can follow this right over here. And so this resource is really straightforward. It's just there to help you to be able to walk through these steps. But the same thing here, it says sample size, standard level, desired level of confidence, and the population or sample standard deviation. Okay. Right here, we have sample size, which is degrees of freedom, desired confidence, and then we also have the standard deviation, which is S, or standard deviation. And so we have that information right there. And then we, with the sample size, you'll also need N. And if you want to know, right down here, you've got a nice little key. It has N, number of observations in a sample, number of observations in a population, proportion, sample standard deviation, so on and so forth, going all the way down. So you'll see in these equations, they are taking into account the sample size, the desired level of confidence, and the standard deviation, just like what it says right here. So if you know the population standard deviation, you can be blank percent confident, 90% confident, 95% confident, 99% confident that the actual population parameter falls within blank standard deviations of the mean. Okay, so what we have right down here is this is very similar to what we did in Unit 1 and Unit 2, but now what we're doing is we've got a population, we've got a point estimate of a population parameter. So this right here, this orange line, it might be a mean. So I'm estimating a mean. So I've got a point estimate of a mean, but the question is so I've got a sample mean. How confident am I that the actual, that this point estimate of this mean actually represents the population mean? Does this actually represent the population mean? Well, I can be 90% confident that the actual population mean is within this range. You notice right here, blank, right here to right here, that's negative 1.645 up to 1.645 standard deviations below and above the mean. So I am 90% confident that the actual population mean falls within this range. I am 95% confident that the actual, maybe not population mean, but that the population parameter actually falls within this range. I am 99% confident that it actually falls within this range. And when you use z-scores, you're able to do 1.645 plus or minus 1.645 standard deviations of the mean, 95% fall within 1.96 standard deviations of the mean, and I'm 99% confident that the actual population parameter is within 2.576 standard deviations of the mean. Okay. So if you only know the sample standard deviations, you have to use the t-chart or t.inverse.2t, which I also have that right here, t.inverse.2t. So if you don't have the population standard deviation, then you, instead of the z-score, you use t.inverse.2t. Okay. And then for the probability, you use 0.01 for 99%, 0.05 for 95%, and 0.1 for 90%. And then the degrees of freedom, which is n-1 for this. And then if you know how accurate you want to be, but have not gathered a sample, you can calculate how large the sample needs to be in order to have the accuracy you want. And this depends on the max allowable error. In other words, how much are you willing to be off by? Standard deviation, and the desired level of confidence, or the z-score, or the z-score for the desired level of confidence. Okay, so the point estimate of the mean. So what we're going to do right here is we're going to do an example really quick. A sample of salaries from 84 professionals in the US was taken. So what I've got here is I have a lot of salaries from different jobs. I have 925 salaries from different jobs in the United States. Okay, and so what I did is I just took a sample, a random sample of 84. Let's see, where did I put that? 84. And so I have the value of 84 jobs, and I calculated the mean and the sample standard deviation. And so I put it right here. And so we've got the sample mean and the sample standard deviation. And so I put it right here. And so we've got the sample mean of 6,000 or 66,450.48 with a sample standard deviation of 23,257.79. So I'm going to put this right here. 66,450.48. Okay, so this is my estimation of the population mean. That's the whole point of what we're doing. I'm estimating the population mean, and my best guess estimate of the population mean is the sample mean that I just took. Okay, so I took a sample mean. This is my best guess estimate of the population mean, but the problem is I know that I might be off by a little bit. Well, how much might I be off by? Well, that's called the margin of error. So the margin of error says, okay, if I want to be 99% confident, I'm going to be off by this much, or I could be off by this much, or I'm 99% confident that it's within these two values plus or minus the, that it's this value plus or minus the margin of error. Okay, so the margin of error, in order to calculate the margin of error, it is the z-score. Hold on, I'll pull it up in this super cool thing. So for the margin of error, we're coming right here. So we've got the z-score, we've got the number in the sample. So let's first of all take the mean. So the mean okay, so the mean is going to be, whoops, that's not what I want, 66,000. Okay, the number in the sample, which is going to be 84. Okay, the z-score, and for this z-score in particular, I want 2.576 because I know that I can be 99% confident that the actual population mean is within this confidence interval. So 2.576. Okay, and then the standard deviation of, do I want 23,000? No, what I want is I actually also put in here the population standard deviation. And so if we're estimating the population proportion, or sorry, the population parameter, we want to use the population information. Always use the population information if you have it. So now what we're going to do is we're going to do equals the standard deviation divided by the square root of the size of the sample. Okay, and so this right here gives us the standard error. Okay, And then in order to get the margin of error, so the standard error, remember, is very similar to the standard deviation, but we're dealing with samples, okay? So if I take every single possible sample of 84, on average, they differ from the mean by about $2,668.01 or 2 cents. Okay, so now what I'm going to do is do equals 2.576 multiplied by that standard error. Okay, and so this is the margin of error. So the margin of error is saying, okay, I want to be 99% confident. I am 99% confident that the actual population mean is 66,450.48 plus or minus 6,872.81. Okay, so that's the margin of error. And so this margin of error says, okay, I might be off in my estimation, in my 99%, in being 99% confident. I am 99% confident that the actual population mean is 66,450 plus or minus 6,872. Okay, and if I want my 99% confidence interval, it would be the upper value. Let's do the upper value. So equals plus. Okay, so we've got 73,323.29. It's right here. Okay, and then we'll do it on the other side as well. So for the lower, we're going to do equals 66,450 minus that right there. And so we've got 59,577.67. So I am 99% confident that the actual population mean is between the values of 59,577.67 and 73,323.29. Okay, and so that's this right here is the lower limit. Okay, and upper limit. Okay, and so we've got the lower limit and the upper limit for the confidence intervals. And this is how we would go about doing it. So in other words, we are estimating this point estimate, and we're saying, you know, the actual population mean, we are 99% confident that this is the actual population mean, give or take this amount. Or we are 99% confident that the actual population mean is within this range of values. And so if you were to, just imagine, instead of guessing one, you know, a really specific number, you're guessing a full range of numbers is what you're doing, or you're estimating a full range of numbers. Now, if you want the margin of error to be 2,000 instead of the 6,872, what is it that you can do? Well, that's a really great question. Well, if you still want to be 99% confident, let's just come over here. We're calculating the needed sample size. Well, we've got the standard deviation right here. So we've got the standard deviation. Let's just do equals. Okay, and then we've got the z-score of 2.576, and then the max allowable error of 2,000. And then the needed sample size is going to be equals the z-score multiplied by the standard deviation divided by the maximum allowable error, and then don't forget to square it. And so the needed sample size would essentially be 992, because you always got to round up. And I would just say sample 1,000 at minimum. And so 992 or 1,000, but on the exam, you would put 992 would be your needed sample size in order to have a maximum allowable error, or a margin of error, if you will, of 2,000. And so that's how you would go about doing that. And so for here, like I said, 992, you would just put would be your sample size, control underline, and then yeah, you can fill in all the rest. So this is essentially why we use the 1.645 plus or minus 1.96 and plus or minus 2.576. Conversely, if we were to have t values instead, okay, using t dot inverse dot 2t, okay, this 1.645 and all these values, what would they be instead? Let's put this right here. Oh, that's not going to work. This is what happens when you anyway. So we'll just do the negative sides. So equals t dot inverse dot 2t. Okay, and we're going to do 0.01, and the degrees of freedom is going to be 84 minus 1, so that's going to be 83. And so this is going to be 2.63. So negative 2.636. Okay, next, we're going to do the same thing. Equals t dot inverse dot 2t, and we're going to do 0.05, and the degrees of freedom is going to be 83 again. And so it's going to be negative 1.989. Okay, and then last but not least, we are going to do a 90% confidence, so equals t dot inverse dot 2t, and we're going to do a probability of 0.1, and then the degrees of freedom is 83, and so 1.6634, so negative 1.6634. I don't know what just happened to that there. Oh, there we go. Negative 1. Or just negative 1.663. And so you'll notice instead of using 2.576, use 2.636. And the only reason why I didn't put it over on this side is because all this stuff is in the way. And then negative 1.98, and you'll notice that the ranges are just a little bit wider because it's not quite as accurate. And so because these aren't quite as accurate, they're going to be with a, basing it off of sample data, the sample standard deviation and whatnot, it's going to just be wider to account for a little bit more error. And so instead of 2.576, you're going to be using these t-scores. And then these are the z-scores right here. Let's do this. Z scores, T scores. Yeah. And then there we go. So that's how you would go about doing this. And hopefully this adds a lot more clarity to what it is that you're doing. And if you have any questions, feel free to reach out. Thank you so much.